Here we go. By the end of class today, you will be able to describe what Coulomb's law is and use Coulomb's law to calculate the net electric force. Woo! Isaiah. Coulomb. Coulomb. Yep. All right. So this question is coming from the reading that the pre-quiz that you had Friday. So if you took notes, pre-quiz for Friday, that's where you're going to get that stuff. Correct answer is D as in dinosaur. Dangerous dinosaur. Okay. Here's a big difference between chemistry and physics. In chemistry, you looked at individual atoms. And you would count the number of electrons. Like for sodium, you'd be like, oh, it wants to lose an electron to be happy. And so it would have a charge of +1 because it has one more proton than electrons. Chlorine would want to gain an electron. So it would have one more electron than proton, therefore it would have a charge of -1. That's just a counter. The problem with this process, or this way to do it, is in physics, we're looking at macro size objects, things that you can hold in your hand, things that have trillions of atoms. Good luck counting those. Like 1, 2, So that's like trying to measure from here to California in inches with a little ruler. Like that's just stupid. Okay, we need a bigger unit. Okay, and that's where coulombs come in. Okay, here's kind of a lame analogy. We measure the number of eggs in terms of a dozen. If I give you a dozen eggs, you're like, oh, I got 12 eggs. The dozen package, or the package that extra electrons or extra protons come in, is a coulomb. The size of that egg carton is 6.25 times 10 to the 18th number of extra electrons or extra protons. Okay, the reason why it's not C is because you need an extra, like if you had this many protons as well, you'd have a neutral charge, but this would give you a -1 coulomb. Okay with that? Okay. Coulomb, this is different. You've never seen this before. Last semester when we said, hey, displacement's measured in meters, you're like, I know what a meter is, ish. And like time's measured in seconds, like got that on lockdown. Mass, kilograms. That's a European thing, but okay, I get it. Coulombs, no framework. Like you've never seen that before. It's just wacky. That is the unit for how much charge something has. Chemistry, you just counted. You didn't say it just has a +1 plus. In physics, we say it has this much amount with a unit of coulombs. Try that one. So you don't need a calculator. Just use process of elimination. Tell your neighbor. All right, ready? If I gave you 2 eggs, how many dozen would that be? If I gave you 2 eggs, that would be 2/12, right? That's 1/6 of a dozen. Not even a dozen. If I gave you 2 extra protons, that is 2 over 6.25 times 10 to the 18th. Because that's how big our carton is. Correct answer is C. Okay, so listen. You see how there needs to be a transformation from chemistry mindset to physics mindset. Okay, we're not counting individuals anymore. We're taking it in terms of chunks. We're measuring how many eggs we have based on how many dozen, not how many individual eggs. The dozen now is just huge. Okay, or that. Sort of, kind of, maybe, sort of. Hopefully, get used to it. All right. All right. So, thanks, Josh. Okay, I've got a Coke can. It's neutrally charged. Okay. Stay. Charging the rod, negatively charged. Stop. Oh, it likes that way. Oh dear. Okay, so what's going on inside of this neutral aluminum conductive can? Why is that being attracted? What's going on inside the charged particles inside the Coke can? And so electrons polarizing, meaning which way are they going? They're going away from the rod. Okay, so here's your Coke can, here's the rod, it's negatively charged. The electrons are like, ah! They're going away. They're being repelled. However, the can is rolling towards. Why? Why is it being attracted? The protons are closer. It's a smaller distance than the electrons now that it polarizes. So the overall force, the total force, is going to be attracted because the force of attraction is greater than the force of repulsion simply because the electrons are further away now. With that. And that's why neutral objects, when polarized, attract. Okay. Give this one a shot. Tell your neighbor. Correct answer is. Correct answer is D. Dangerous dinosaurs. They have to be the same charge because they're repelling. Good with that? Okay. Correct answer is. Good job reading the top caption there. If you know Newton's third law, you're like, boom, force on the moon is equal to force on the earth from each other. Talk to your neighbor.
Yeah. Wait, which one? Yeah. Oh.
Okay. Here's some insight. Correct answer is D. That's a good adjective for dingoes. Dropping dingoes. I don't know. Dancing dingoes. All right. Okay. So they have to have the same force because of Newton's third law. Okay. If this would become more positively charged than it already was, there'd be a greater force of repulsion on both of them. Good with that? All right. Okay, we know that they have the same type of charge. We've already established that. But what this question is asking for is which one has the greater amount, or like how do their amounts of charge compare? Tell your neighbor. Correct answer is C. Bless you. Just like here, they experience the same force, but they have different charges. You don't know which one has a greater force. Sorry, greater charge. Good with that? Okay. I want to find the electric force between spheres A and B. Here's a bunch of characteristics about the different chart or the different spheres. I want to know the electrical force based upon this equation. Which information I'm going to employ to be able to calculate the electrical force using Coulomb's law. Hopefully you said charge of A and B, or 1 and 2. Which one's 1 and 2? Doesn't matter. Okay. And then D is the distance of separation between the centers. Make sure you square that. Okay, go to that. K is a constant, 8.99 times 10 to the ninth. Regardless of what the scenario is, it's a constant. Okay, go to that. All right, so example problem. You got it. Peanut has a charge, packaging peanut has a charge of -3 microcoulombs on it, and a clear strip has charge of +15 microcoulombs, and they are 30 centimeters apart. How much electrical force is acting on them, and which way is the peanut being forced? So first off, 1 coulomb of charge is actually a pretty big amount. Just to give you an idea, a lightning bolt is somewhere between 10 and 20 coulombs. Okay, so having 1 coulomb of charge, a little on the risky side. So in the lab, what we do is we use microcoulombs or nanocoulombs. Okay, but when we do the math, we need to convert that to coulombs, just like if I gave you kilometers, you need to convert that to meters. Okay, quick review. Micro times 10 to the -6th. Nano times 10 to the -9th. Okay. So we are looking for the electric force. There's our equation. Electric force is 8.99 times 10 to the 9th times 3 times 10 to the -6th coulombs times 15 times 10 to the -6th coulombs. I recognize that that is improper scientific notation. However, it is not illegal to write it as such, just whatever. And then 0.3 meters, remember to square that. Okay. One side note before we start plugging things into the equation. notice, well, first off, micro, that's where the 10 times 10 times 10 to the negative 6 came from, converting that to coulombs. Secondly, in the equation, drop positive and negative sign. Okay, when doing the math, drop the positive and negative sign. Okay, we ignored it. So if you're like, oh, that gravity stuff was a struggle, plugging it in a calculator, you might want to plug it in right now, see if you get it right. That's what you should get. Okay, what's the unit? What? What did you say? Newtons. It's a force. Remember, square the radius.
I can still see that. I just got it times 10 to the 16. You squared the whole thing, didn't you?
No.
I didn't like almost there.
Did you do times 10 to the negative 6 on both of those?
I think so.
Try it again. All right, so that's the strength of the force. Okay. Now, which way is the peanut being forced? So is this going to be attraction or repulsion? How did you know it was attraction? This is where you look at the charges, the sign on the charges. You're like, hey, look, they're oppositely charged. They must be attracting. Okay, so which way is the peanut being attracted? Right or left? Left. So this is 4.495 newtons to the left. You could say attracted to the left, but really the to the left is what I really care about. The strip is being attracted at 4.495 newtons to the right. But all I asked about was, the peanut. Good with that? Okay. So, there you go. Questions there? Okay. Get figured out.
Yeah, I got it. Just doesn't know. I don't know.
Okay, give this question a whirl. Tell your neighbor. Not yet. This chapter. All right. So the equation only has two charges. Okay. So what you need to do is take it in pairs, with 2 always being part of the pairs. Okay. What's going on between 1 and 2? They are repelling, yes. Which way is 2 being repelled? Okay. Which way? What's going on between 2 and 3? Attracting. Which way is 2 being attracted? To the right. Okay. The total force, the net force, if is what? To the right or left? Right. If it was 3 newtons to the right and 2 newtons to the right, what would be the net force? 5 newtons to the right. Let's find the resultant. Good with that? All right. Now, what about object 3? Net force on object 3. Tell your neighbor. Correct answer is B, to the left. Now, check this out. Between 2 and 3, you have attraction. So 3 is being attracted to the left. Is 1 exerting a force on 3? Is 2 interfering with that? Is that influencing what 1 is exerting on 3? Okay. When I was in high school, I thought it did. I was like, well, it's like running interference. It's like getting in the way. Okay, so this ball has a force of gravity on it, right? Okay. I'm going to put this envelope. I'm separating between Earth and the ball. Oh, interference. You can't get me. Oh, I can. Oh, still drop. Does this envelope at all affect the force of gravity on the ball? No, even though it's between the Earth and the ball, it doesn't do anything. So the fact that 2 is here does not do anything to the electrical force between 1 and 3. Okay, so to calculate that, we would simply just ignore that completely, and we would say between 1 and 3, there's a force of attraction going that way. The net force is to the left. Good with that? Okay, now we're looking at the net force on object 1. Tell your neighbor. All right. Correct answer is. Okay. If they had the same charge, one and two are repelling, and one and three are attracting, which force do you think is going to be stronger? The one from two or the one from three? One from two would be stronger because it's closer. Oops. It's closer. Okay. But because we don't know how much charge there is it possible for this force to be greater than this force? Tell your neighbor how that would be. Okay. If three was big enough, that could overcompensate. So we don't know. D.
Yes.
Okay. Good with that? All right. I will give you a couple minute head start. You're finding the net electric force on object C. Go. 8.99 times 10 to the 9th.
You do you, bro. Just hold your horses. Yeah, dude. Yeah, dude.
Nope. They are both positive. Same type of charge.
Yeah. That's what I meant. What do you mean, like something? Dog. Come on. That's what you're smiling, bro. You gonna catch your smile tomorrow? Yo.
Like it's being more attractive. Being more attractive. Being more attractive to A.
Alright.
Here we go. Okay, I'm going to do between A and C first. We got 8.99 times 10 to the ninth times 14 times 10 to the negative 6 coulombs times 7 times 10 to the negative 6 coulombs over 0.5 meters. Make sure you square that. Find that to be 3.5 newtons. Between B and C, 8.99 times 10 to the ninth and you find that to be 2.8. Okay, those are the individual forces. Okay, good with that. Now, finding the net force. Ready for this? Here are the two popular errors. First error, do not, listen to this, do not associate attraction with a positive force and repulsion with a negative force. Do not say, oh, it's attracting, that's a positive force. Oh, negative, that's a negative force. Don't do that. The second error is to include the negative signs in the math, and so you get a negative value here. Don't do that. Okay? Once you get these values, then look at the scenario and say, all right, between A and C, it's being what? Attracted or repelled? It's being attracted. So C is being attracted which way? To the left. Between B and C, what's going on? Repelling. Which way is C being repelled? To the right. You see how I did that? So the net force, tell your neighbor. What is the net force? They're going in opposite directions. So you're subtracting them, and you have 0.7 newtons to the left. Okay? Personally, I'm going to make you do right and left. I'm not going to say positive or negative direction. You will have to do that on mastering. But for me, I feel like that could be easily mistaken for positive charge, negative charge. So I'm going to keep positive and negative for charges. And for direction, I'm going to say to the left, to the right, up, down, something like that. Okay, good with that? All right. You have a worksheet due tomorrow.